Good day, everyone. We are Group 1, and we are presenting our automated spreadsheet designed for the bisection method, which helps find the roots of a given function.
Moving in on our spreadsheets, the first thing that we can see is the section where the user can input the set of values. So we have here the given initial values, which are -6 is the initial value of A, and 2 is the initial value of B. In the lower part of the initial value of B, we can see that there is an epsilon and C prime. So in the epsilon, we choose a number that is closer to 0, which is 0.001. It is the stopping criteria where if the absolute value of the change and C, which is current value, minus the previous value is less than or equal to epsilon. The current value of C is accepted as the approximately root. In C prep, we choose a large number which is 99999 because in the first iteration there is no previous C. So it's there as a dummy variable. So we have here 8 rows, which consist iteration number A, B, C, f of A, f of B, f of C, and the decision. We start by setting initial values for k variables, A, B, and epsilon, which shows the allowable error. These inputs are crucial for narrowing down the interval where the root is. Using the given formula, group 1 underscore function. We find the function's values at these points giving us f of a and f of b. Next, we calculate c by taking the average of a and b. This is done using the formula c is equals a plus b over 2. Then, we evaluate the function of c to get the f of c. In the next step, we use a formula to decide whether to replace a or b with c, based on whether f of c is positive or greater than 0 or negative less than 0. In first iteration, the formula is if absolute number f of 6 minus b5, which is the c minus c prep is less than or equal to b4, which is the epsilon. Since there is no c prep in the first iteration, we use the value 99999. We set as the c prep. If I6 is greater than 0, the decision is B replaced with C, and A replaced with C is less than 0. In the second iteration, and the rest of the formula is equals to if absolute number current C minus previous C is less than or equal to B4, which is the epsilon, and the decision is stop. If f of C is greater than 0, the decision is B replaced with C, and A replaced with C if less than 0. In our data, the decision appears to stop iterating at the 17th iteration.
Proceeding to the graphs, let's have first the scatter plot. We visually track how many times A and B are replaced with C until we reach the stop condition. And the next graph is line graph. In the line graph, we plot the values of A, B, and C throughout the iterations. Each line is color coded for clarity, helping us track the changes more easily. Next is bar graphs. These bar graphs represent the relationship between iteration and function values. The first graph illustrates the function f of c, with the x-axis showing the iterations and the y-axis depicting the corresponding function's values. Second graph depicts the process of finding the value of c, with the x-axis again representing iterations and the y-axis showing the values involved in the calculation. These visualizations help understand how the function values change over iterations and the convergence towards a specific value for C. In conclusion, our automated spreadsheet using the bisection method offers a systematic way to find function roots accurately and efficiently. By using formulas and visualizations effectively, we've shown how our tool simplifies the process, making it easy for users